Okay, welcome to the lecture for Friday, 10/17. This is class day 23, and we're doing the review chapters 6 through 10. Let's first look at, let's see, sorry. Let's first look at the syllabus, and I guess I already lost my place here. And let me do this. Okay, so this is Monday, October 17th. So I scheduled live presentations. I didn't really schedule a lecture for today, and we're going to do those live presentations on Wednesday. Be sure you come to class on Wednesday. Be sure you come tomorrow and get help at noon if you need it. And watch the video I did for Friday that I just now did, but I'll post it. I haven't posted it yet, but I will. And look at that, and that'll help you give you some hints on how to set up the Logisim simulator. Okay. So homework 10 is not due until next week, I guess, the 21st, or maybe that's 17th. That's Friday. Okay. All right. So, okay. And everybody will present on Wednesday. And make sure you do the end of chapter 10 quiz by Saturday. That was last Saturday. Oh, yeah. So you should be doing quiz 11. Yeah, quiz 11. That's next week. Oh, yeah, I don't think you have to do quiz. So there's no more. There will be a quiz for this Saturday, I'm pretty sure. Okay, let me look. If we go down to the end, this gives you the whole table. So end of chapter quiz. Quiz closes on Saturday. So quiz 10 closed on the 15th. That was Friday. And then, you don't have a quiz until November 5th. And you have 2 on November 5th. That's goofy. Anyway, so we'll cover chapter 11. I'll start on that on Friday. I'll start on that after the test, which will be a week from this Friday. That'll be pushing it a little bit. Okay, so that's how we'll go. It'll open up the 29th, and you have to do it by the 5th. This will open up the 3rd, and you have to do it by the 5th. All right. Okay, so what I'm going to do now, I'm going to work a test, and so for that, I'm going to, I'll switch to the paper here, and we'll just go through this test, and so let me just go ahead and talk about this a little bit. Okay, so first off, I'm definitely going to ask you questions about taking a truth table and putting a truth table. Yeah, sorry, let me get this set up a little bit. I don't know. Okay, can you see me there? Sort of. Ouch, not too bad. All right, can you see me there? Let's see. Yeah, that's pretty good. Okay, so hopefully that'll work. All right, so let's go through this. Okay, so you're definitely going to have questions about being able to take this truth table and go through it and identify it. So first off, I may have you. I may ask you about min terms. I may ask you about max terms. But one thing, remember, when we have a 4-variable a truth table and a 4-variable K-map, we number the squares. So this is box 0, that's box 1, but we reverse these. That's 2, that's 3. This is 4, that's 5. This is 6. Oh man, sorry, totally screwed this up. Hang on, I'm not going to leave that like that. Okay, let's try this again. I don't know, my brain must have snapped. All right, so this is box 0, which stands for row 0. This is box 1, which comes from row 1. This is box 2, which comes from row 2. 3, which row 3. And then 4 here. 5, 6, 7, and then we skip over here. 8, 9, 10, 11, 12, 13, 14, and, oh my God, 14 and 15. I can't believe I did that. All right, it's because I'm slightly distracted. All right, so this is row 2, 3, 4, 5, and notice 0, 1, 0, 1. That's 5. This is 6. That's 7. So the numbers over here match the binary value here. This is 8, 1, 0, 0, 0, 9, and then I'll just go right. A, B, C, D, E, F, 4, 10, 11, 12, 13, 14, 15. I'll just write these in hex. I wrote these in decimal. Doesn't really matter. You can use hex or decimal, either one. Okay, now what I need to do is to map the truth table into the K-map. And we've gone over this a number of times, but I just want you to make sure you can do this. So we have a 1 here, so we put a 1. Now I'm not going to put the 0 in, but because it's blank, you know it's a 0. And then 2, it's a 1. 3, it's a 1. 4, it's a 0. 5, it's a 0. 6, it's a 0. 7 is a 1. 8 is a 1. 9 is a 0. 10 is a 1. 11 is a 1. 12 is a 0. 13 is a 0. 14 is a 1. Oops. 14 is a 1. And 15 is a 1. So hang on. Okay. Picking up where we left off. Yeah. Yeah. Okay. All right. So we put 10 in. No, we needed 14 and 15. 14, 15. All right. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8. 8 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I missed one. Let's look at it and see where I got it. So 0, 1, 2, 3, 4, and 5, and 6 are zeros. 7 is a 1. 8 is a 1. 9 is a 0. 10 is a 1. 11 is a 1. Oh, that's where I ran out of ink. Okay. And then 12, 13, 14, 15. Okay. Everybody good with that? All right, so we have 9 ones here. We have 9 ones there. And all the rest of them would be zeros. Now, if I had a don't care, I would put the don't care in with the ones. And then I'm just going to go ahead and put the zeros in down here since I can already see. So this is a 0, 0, 0. I'm not going to number the boxes down here. I just want you to do this one time. Normally we're not going to number the boxes. All right, and there we go. All right, so let's do the prime implicants with the ones here. All right, so the first one that's pretty easy to see is this group of 4 right here. The next one that's pretty easy to see is this whole row. And the next one is the 4 corners. Now, of these, let's identify all the ones. I'm going to put a little check mark on the ones that are only covered by a single group. Well, okay, so what about this one? Yeah, so there is actually another group of 4 right here. Yeah, that would also be a group of 4. All right, so now let's see. Okay, so only covered by 1, only covered by 1, only covered by 1, only covered by 1. Notice that the ones in this last group of 4 I drew, all the ones in there are covered by at least 2 loops. Okay, so let's write down. Let's first count how many we have. We have the 4 corners, and we always know the 4 corners of B prime D prime. And then we have this row. That's going to be CD. Then we're going to have this group of 4. That's going to be A, because this is A. And then the middle 2 rows are B. And the bottom 2 rows are C. And the middle 2 rows are D. So this group is going to be AC. So we'll write AC here. And then, so that takes care of the four corners, this row, that group of four, and that final group of four, this wraparound group of four, is going to be B prime C. Okay? So it turns out this final group, this B prime C, is a consensus term. But all the rest are essential because I have a 1 here not covered by any other ones, a 1 here, so that makes the four corners needed. This makes this row required, and this makes this group of four. But this group of four, the B prime C term, all these ones have at least two different groups covering them. Therefore, they are not essential. They're non-essential, and that makes them a consensus term. So our final solution then would be for the SOP solution would be the SOP solution would be F equals B prime D prime, the four corners, CD plus CD, the row, plus AC, this group of four right here. All right, now we don't need the BC term, so we're just going to leave it out. Now we have, what about the max terms? Well, we have one group of four here, a row here, and a wraparound group of two here. So we have 1, 2, 3 terms here as well, but one of the terms is going to have 3 variables instead of 2. So this row, we'll write it if it were ones, and we'll invert it. So if these were ones, that would be C prime D, which turns into C plus D prime. And this group of four would be B C prime, which turns into B prime plus C. And finally, this wraparound group would be, if they were ones, we'd write A prime B C prime. But they're not. They are, in fact, zeros. So we're going to have to invert this, and we're going to get A plus B prime plus C. All right? So our final POS solution is going to be B prime plus C quantity times C plus D prime quantity times A plus B prime plus C. Now, you can see that this has 1, 2, 3, 4, 5, 6 inputs plus 7, 8, 9 for the final output OR gate. So 3 input AND gates, 3 2 input AND gates, and 1 3 input OR gate for the output. And this has 2 2 input OR gates, 1 3 input OR gate, and 1 3 input AND gate for the output. So this is a little more expensive, so this is simpler. So this one is the simplest. The SOP is simplest. And then this is the POS form. So this pretty well works this whole problem. All right. Okay, I think that's good. Now the next thing I want to do, so which solution would be the least hardware? Well, the least hardware would be the SOP. Realize the switching function using a multiplexer. Okay, remember how we do that. So first, where's the switching function? Here it is. We've listed the min terms here. So it's 0, we get a 1. 1, we get a 1. 2, we get a 1. Not 3, not 4. 5, we get a 1. Not 6. 7, we get a 1. And then we get 15, not 14. 13, not 12. 11. And then not 10, not 9, not 8. Okay? So we have 1, 2, 3. Oh, sorry, 0, 1, 2. 5, 7, 11, 13, 15. Right, and that's correct. 0, 1, 2, 5, 7, 11, 13, 15. All right. Now we're going to do the pairs of rows. So let me draw that out. So we're going to do this pair. Maybe I'll use a pen or something. Okay. So for the first pair, we have two ones. So this is going to be I0, and it's going to equal 1 because they're both ones. This is going to be I1, and it's going to equal D prime because it's opposite to D. D goes 0, 1, this goes 1, 0. Here we have 0, 1, so that's going to be I2, and that's going to equal D because it goes 1, 0, 0, 1, and this goes 0, 1. Here we go 0, 1, so that's going to be I3 and another D. This is going to be 0, 0, so that's going to be I4, and it's going to equal 0. And this is going to go D again for I5, D again for I6, and D again for I7. So 1, D prime, D, D, 0, D, D, D. And then here, our address lines, A2, 1, and 0. This is the high line. This is the low line. So we want to connect A, B, C to that. And of course, D finds its way in over here. We don't have 4 control lines. We only have 3 because it's an 8 to 1 mux. And there's our output F. Okay, so that's how we solve that. All right, moving on. Okay, we have here a, let me blow this up a little bit. I'm bringing this in. Okay, that's a little better. Okay, what kind of flip-flop? Well, it's pretty obvious. It's a D flip-flop. And does it have an asynchronous input? Yes, it's got a set. Is the set active, high, or low? Well, since there's no bubble, it's active, high. So when it's 1, the set's asserted. When it's 0, the set's not having any effect at all, and we're dependent on the clock. Is the clock a rising edge or a falling edge? Well, in this case, because of the presence of because of the caret, it's an edge, not a level clock, and because of the bubble, it's falling. So this is a falling edge clock. It's a D flip-flop. It doesn't have a clear not shown. It has a set. So I guess the answer there would be no. But it does have an asynchronous input. Is the asynchronous input active, high, or low? It is active, high. All right. Okay. Now, given the following gates, show how to replace the gates having only 2 inputs max. Okay, so with this gate, it's really easy. You just have to have 2 OR gates for the input, and then you have to have an OR gate here. So of course it does add a layer, but it's really easy. You just put in the 2 inputs here and the 2 inputs there, and now you're implementing it with gates only having 2 inputs. However, when you use a NOR gate, that's a little different. Now we'll have 2 NOR gates, but with bubbles on them. And you put 2 of the inputs in here, the other 2 in here. These come out, and now you have to go through an inverter, and then you can go into the final NOR gate. And this then gives you, this then is equal to this. This, however, is equal to this. Without the bubble, it's much simpler. With the bubble on the output, you have to put these inverters in. All right. Now we have we want to write the minimum circuit represented by the K-map. Okay. So in this case, how can we do this? Well, it's really easy. You should be able to see this immediately. You circle these 2, circle these 2. And then you do have this consensus term here, which I'm going to loop, but we're going to ignore that for the moment. So we need this group, so that's going to be B. A drops because it's 1 here and 0 there. C prime, D prime. And this is going to be A prime, B, and then it's D because it's in the middle 2 rows. D. oops, D. So A prime B D. This consensus term would be A prime B C prime. All right. Now, so draw the circuit represented with only 3 gates. Well, in this case, then we wouldn't use a consensus term. We don't have to have it. We don't need it. So the circuit would be an AND gate here, an AND gate here. This would be B, C prime, D prime, and this would be A prime, B, D. And these would go into one output OR gate, and that's your F. And on the map, the transition that could cause us a hazard would be from this box to this box, or maybe from this box to maybe vice versa. So it's the transition between these two boxes, and that's because you're changing from this controlling AND gate to this controlling AND gate. And the problem is, in this no, there's a problem here. Hang on. Let me redraw this. Yeah, let's do this right here. Okay, we'll draw a bigger map. I made some mistake there. All right, and so I believe we had those two. Let's see. One, two. Yeah, okay. So, A, B, C, D. We had 1, 2, 1, 2. So we have this group, and we have this group. So this group is going to be B, C prime, D prime. This group is going to be A prime, B, D. All right, so notice the D here changes from D prime here to D there. And that's where the hazard comes in. So if we draw this circle, this circuit like this, so we have 2 gates, an AND gate here with B, C prime, D prime, and we have another AND gate here with, say, A prime, B, D. But let's say our D comes from over here, and it has to go through an inverter. And so our D prime comes from there, but our D comes straight in. Okay? And let's say we have 5 nanosecond delay, 5 nanosecond delay, and 5 nanosecond delay. Well, let's have the situation where D equals 1 and B equals 1, C prime equals 1, or C equals 0, and A equals 0, or A prime equals 1, however you want to write that. So we'd have a 1, a 1, and a 1, and here we'd have a 1, a 1, and a 0. Then let's say that after about, so our output, and then these go into another OR gate, and here's our output F, and we have another 5 nanoseconds. So if D changes, here's the problem. So D equals 1, but then it goes to 0. Well, so let's draw, we'll draw D and we'll draw F, okay? So right now, F is a 1. So F is a 1, and then let's say out here, D changes from a 1 to a 0. All right, well this 1 becomes a 0 immediately. But this 0 stays here for 5 nanoseconds before it changes to a 1, because there's a 5 nanosecond delay in this inverter. So so if we plotted, here, let's plot a little bit more. We'll do let's do it like this. We'll do F down here, we'll do D, and we'll label the output here J and L. Okay, so here's J and here's L. Now at the start, F is a 1, and then let's say here at 5 nanoseconds, D changes from a 1 to a 0, and it stays that way for the remainder. Okay, well, so what happens then is 5 nanoseconds later, L, which has been a 1, 5 nanoseconds later, at 10 nanoseconds, L goes down to 0, because D was 1, but now it changed to 0. So when D changes, it changes immediately, and it takes 5 nanoseconds for L to change, and 5 more nanoseconds for F to change to 0, because J is already equal to 0. Well, so J is 0, and J is not going to get to 1 until when D changes. You have to wait 5 nanoseconds before this input becomes 1, 5 more nanoseconds before J becomes 1. So here the J become here the D becomes, the D prime becomes a 1, but it's actually 10 nanoseconds out here before J goes up to be a 1, and it stays up, but you have to wait 5 more nanoseconds before F will go back to 1. So what happens then is 5 nanoseconds after, so we go out here, I may be running out of nanoseconds. So 5 nanoseconds here when 5 nanoseconds after D changes, L goes to 0 right here. And so there's a period of time here where L is 0 and J are 0. And that forces F down to 0. And then it doesn't come back up until J goes up. And then there's still 5 more nanoseconds before this comes up. So this is going to be 5 nanoseconds, and this is going to be 10 nanoseconds wide here. So that would be 15, and this would be 20. All right, so the idea then is, okay, sorry, now you can't see it all, but I want to show it to you. All right, so remember, we have our 2 AND gates. We have our D goes through an inverter. It goes straight in over here, but it goes in inverted here. And then we also have B doesn't change, and this is C prime, and this is A prime. So B is 1, C prime is 1, and A prime is 1. The D starts off as 1, but then and this starts off as 0, but then they switch. But because there's a 5 nanosecond delay there, a 5 nanosecond delay, a 5 nanosecond delay, and down in here in our output OR gate, another 5 nanosecond delay, there's a little period of time here because this D does not go through the inverter. This 0 stays 0 for 5 nanoseconds before the inverter changes the 0 to a 1 and puts a 1 in here. So this goes to 1 and this goes to 0, but there's 5 nanoseconds delay between these two, which means then and this is J and this is L, which means then that that our J is delayed from going to 1 for 5 nanoseconds after this gate already puts a 0. So for a short time we have a 0 here and a 0 here, and then about another 5 nanoseconds later we have a 1. All right, and then when the 1 hits, actually I think this is 5 nanoseconds here. I think they're both 5. But in any event, that's what happens. There's actually another little delay here is the deal. Okay, no, actually it should be 10. Yeah, I think there is a bit of a gap. All right, well anyway, the point is this is a hazard, okay? And you fix it by adding in this gate. And since this gate does not contain that gate is A prime, B, C prime. So basically now our circuit becomes A prime, B, C prime, and then you have B prime, C, D prime, and then you have B, A prime, D. Now you have 3 AND gates going into our output OR gate. Notice this gate does not depend on D. Since it doesn't depend on D, this A prime doesn't change, it's still a 1. The B doesn't change, it's a 1. The C prime doesn't change, it's a 1. So this always stays a 1. So F does not have a little glitch and come back up. It just goes up all the time. And the extra gate fixes this hazard because D doesn't show up here. And in our K-map, we can see that the hazard is because of the transition from this group of 2 to this group of 2. This group of 2 representing this gate, this group of 2 representing that gate. And it's the transition. It could be this box, it could be several different things, but anyway. And the hazard will fix it. All right, hopefully that makes sense. I probably belabored that a little bit, but we hadn't really talked about hazards because I think we haven't gotten to them yet. All right, I want to go through. These last couple of problems. All right. So the answer is, what term could you add to fix the problem? You add the A prime, B, C prime term. Okay, given this VHDL code, so you just have to draw it. So we have an A ANDed with B ANDed with C after 10. So A, B, C, 10 nanosecond delay. And then F is A and Y, A ORed with Y. So A and Y in an OR gate. And then these both go into an AND gate along with, E and F, yes. So this is E, this is F, and these go into an AND gate here, and that's H. All right. And I put in some delays and whatnot. I'm not going to really pimp you about that. I just want you to be able to draw the circuit. Okay? This is actually VHDL, not Verilog, but we've gone over Verilog. If we wrote this in Verilog, it would be A ampersand B ampersand C equals E, and F would be A vertical bar Y, and H would be E ampersand F. So it's just a little different. We use ampersands and vertical bars for ands and ors. Okay, hope you remember though. Go back and review those lectures. This is one, find all the max terms. Use the K-map and find all the max terms. So here's the K-map down here. Okay, so we have A, B, C, D prime. Well, A, B, C, D prime. So remember, this is A, this is B, the bottom 2 rows are C, the middle 2 rows are D. So A, B is this column, C would be these 2, and D prime would be that square right there. Because it's D prime is top row and bottom row. And all the rest would be A, B, C. And then this would be D prime. All right? Then we'll do, so that takes there, that one. B, D, C prime. Okay, B, middle 2 columns. D, these would be these 4, and C prime, it's these 2 up here, because the bottom 2 rows are C, the top 2 rows are C prime. And then finally, A prime, C prime, D. A prime, these 2 columns. C prime, the top 4 boxes here. And D. D would be the middle 2 rows, so it's these 2. This one, these of course overlap. So we're wind up with 1, 2, 3, 4. And then, and then it wants you to pull out the zeros. So all the zeros would be like this. You can write them all in. So the zeros would be 0, not 1, 2, 3, 4, not 5, 6, 7, 8, 9, guess that was a 1, 8, 9, 10, not 11, 12, not 13, not 14, 15. Okay. 12, 15. All right, final one. We've been over this before, and so I'm just going to do this. I hope you could, let's see, I think you could see that. Yeah, okay. Let's do the last problem. Well, this problem is convert this from POS to from POS form, which is OR and, to NOR. Well, you just know you do a double inversion, you partially expand this inner one, which is going to give you tick marks on all these, and it's going to put pluses between them. And then you have the final big one that's that has a tick mark there. So that's all there is to that. You've done this before. But I want to spend a little bit of time on this one, and then we'll quit. All right. Here we have a flip-flop. What do you see about this flip-flop? Okay, so first off, what kind of clock does it have? Well, what kind of flip-flop is it? Well, it's a D flip-flop, right? One input, and it's D. What kind of clock does it have? Well, since there's no bubble and there's a caret, so that's an edge clock. It's a rising edge clock. It's a rising edge clock. Move it over here a little bit. And does it have an asynchronous input? Yes, it has a set. Is it active high or low? There's no bubble, so it's active high. Okay? Now, the way we do this, the first thing is we color in where the set is active. Where is the set active? Well, when it's high. Where is it high? So there's our set. It's high here. That's it. So we'll hatch in this. Now we're going to color in all the rising edges, except this rising edge is blocked by the asynchronous set. This is blocked, so we'll block those, but this one isn't. So we're going to just go ahead and make this come down here. This one isn't blocked, so it'll come down here. This one isn't blocked, so it'll come down here. Not blocked, so it comes down here, and not blocked, so it comes down here. I got that one crooked. When this one when this edge hits, D is what? Is it 0, 1? Well, it's 0 because it's 1 here. It's 0 here. Then it goes up to 1, comes back down to 0, stays 0, goes up to 1, stays 1 through this, goes back down, and 0 here. So here, you don't worry about it here because it's blocked, but here it's a 0, here it's a 1, here it's a 1, and here it's a 0. All right? And we know that we're going to have a delay of 10 nanoseconds after the active edge of the clock or when the set's asserted. Well, the set's asserted here. So now we know we could have a change here. Let's see, let me use a slightly different color. Something. Do I have a red one? Yeah, maybe. Yeah. So we could have a change here. We could have a change here. We can't have anything else until here. We could have a change here. We could have a change here. This one's off. It really should come here. So the change would be here. And a change here. Okay? So basically then, we start here. So initially, with our first clock, Q starts off at 0. It's going to stay 0. And here it's going to just stay 0. But here, because it's a set, it's going to go up and be set. Now it has to stay this all the way to here. Now notice, when we take the set away, it doesn't change the output. Nothing changes until the next clock edge. All this going away does is allow the clock, the rising edge of the clock, to have an effect. In this case, D is 0, so it is going to cause it to go to clear. And then it's going to stay down here. Here, D was a 1, so it's going to get set, stay set, still a 1. And here, it's 0, so it's going to go down and stay 0. And that's all there is to it. All right. So hopefully that'll help you. If you can do the things that we just covered, you're good. If you're confused about stuff, then we need to work on it. And I think you could see all that, right? Yeah. Yeah. So there we go. Okay. All right. Hopefully that makes perfect sense. All right. So I want you to, so just review this so you make sure you can work this test just like I did. Make sure you know how to look at a 4-variable K-map or a 3-variable K-map and pull out all the prime implicants be able to identify whether they're essential or whether they're non-essential, which means they're consensus terms. Don't mess up and miss where you can. Don't have a group of 2 where you could have combined it to get a group of 4. That's what makes something prime, is you can't combine it to make a bigger group. Remember, your groups can only be powers of 2. 3 is not a power of 2, so you can't group 3 boxes. 5 is not a power of 2. 6 is not a power of 2. 10 is not a power of 2. So only 1 box by itself, 2 boxes, 4 boxes, 8 boxes. No, sorry. 8 boxes. Yeah, like that. Okay, and 16, obviously, I'm out of fingers, but okay. So, we've talked about. Remember, we've talked about implementing a function with an 8-to-1 multiplexer, with a 3 to 8 decoder, and with a 4-to-1 mux, or with a read-only memory. And in the case of the read-only memory, we can implement a bunch of functions by adding additional columns. We can add additional independent variables by doubling the number of rows with each added variable. In the case of a 3 to 8 decoder, we do have to add an additional OR gate, and then put into that OR gate all the min terms where f is desired to be 1. And we can implement as many functions as we want by just adding additional OR gates. In a multiplexer, we can implement the function, but we need another multiplexer if we're going to implement a different function. All right, I think that's it. So make sure you review this for the test. Make sure you're getting your presentations ready to go on Wednesday. Come see me tomorrow in my office about noon if you are having trouble with your presentations, and look at the video for Friday if you need help to figure out how to do how to work on your simulation in Logisim, and how to use the 16 segment display that I created. What you should do is boot up Logisim and then load up that 16 segment circuit and then save it with a different name. Okay, and then that will be your simulation. Use the push buttons that you can push on, push off, not the ones that you have to hold to keep them as ones, because you can only hold one button. You can't. So you need 3 buttons, and you can't do that with the single one button. Okay, with that, I'm going to stop this recording, upload everything, and send out an email.